Earlier we've learned to take derivatives of lots of different types of functions. In this lesson we will turn our attention to exponential functions. We do know that the most convenient base for exponential functions is the irrational number base e. The convenience of this base is primarily because if f of x is equal to e to the x, then it's its own derivative. So the derivative, if f of x is equal to e to the x, then the derivative of f of x is e to the x. That turns out to be a very convenient property, which I've summarized here. In general, if we apply the chain rule to that, we have the formula on the left which says the derivative of e to the u is equal to e to the u times the derivative of u. That's basically the chain rule or the general power rule applied where u is some function of x. In particular, if u is equal to x, we'll get what I mentioned earlier. The derivative of e to the x is just e to the x. So it's a function whose derivative is the function itself. It's a pretty nice property. The examples turn out to be pretty simple because the concept is pretty simple. For example, if I ask you to find the derivative of f of x equals e to the 2x minus 1, find f prime of x, you would simply treat the 2x minus 1 as the u in the formula above on the left. Then you would write the derivatives being e to the u, where u is 2x minus 1, so it would be e to the 2x minus 1, multiplied by the derivative of the exponent. Well, the derivative of 2x minus 1 is just 2. Normally we write the 2 in front, so if you simplify it and write it in the most natural way, you would get f prime of x is equal to 2e to the 2x minus 1. And when you get good at this, you can just realize that you're going to have a multiple of 2 when you start and write the 2 in front and be done with it without all the intermediate steps. So part of your goal is to get good enough at this so that you don't have to show as many steps maybe as I'm showing in these examples. Let's do another one. If y is equal to x times e to the 2x minus 1, find y prime. Well, here you have an exponential, but it's a factor within a product rule. So the first thing you have to do is realize that x is like u in the product rule and e to the 2x minus 1 is like v. So you have a product of two things, one of which happens to be an exponential. But the product rule applies first. So x is like u, e to the 2x minus 1 is like v. The product rule says you take u, which is x, times the derivative of v, which would be the derivative of e to the 2x minus 1, plus, then you reverse it, take v, which is e to the 2x minus 1, multiplied by the derivative of u, which would be the derivative of x. Going back now, you can see as you start, you've got x times the derivative of e to the 2x minus 1. Well, when you get to the derivative of e to the 2x minus 1, you've got to use the rule on the left for derivatives of exponentials. The derivative formula for derivatives of exponentials says you take the exponential written down as it is, multiplied by the derivative of the exponent, plus, then you've got e to the 2x minus 1 multiplied by the derivative of x. Well, of course, the derivative of x is just 1. Probably want to clean that up a little bit, maybe put the 2 in front of the x. You've got 2x times e to the 2x minus 1, and then, of course, when you multiply something by 1, it doesn't change it, so that's just plus e to the 2x minus 1. So the actual exponential derivative rule is extremely simple, but as you can see, it can be embedded in a different rule, so they can all be mixed together. So the thing you should be doing always really is just practicing a lot so that it becomes second nature. Let's do another. What if f of x is equal to e to the x divided by x, and we want to find the derivative f prime of x? Well, this time you have an exponential in the numerator, but basically this is a quotient rule. So remember, the quotient rule, the way I think of it, is high over low. So the derivative of high over low is low d high minus high d low over low low, or low squared. So you've got low times the derivative of high minus high times the derivative of low over low squared. Well, low is x. then you got to multiply that by the derivative of high. Well, high is e to the x, that's the derivative of e to the x, minus, then you reverse it, you take high, which is e to the x, multiplied by the derivative of low, that'd be the derivative of x, all over low squared, which would be x squared. Again, remember, the derivative of e to the x is just e to the x. You can see that formula on the right up top where I said the special case is if you get the derivative of e to the x, you just get e to the x because the derivative of x is 1. And of course, when you simplify all that a little bit, you'll end up with x e to the x minus e to the x all over x squared. So you have these exponentials, in this case, embedded in a quotient rule problem. I might ask additional questions. For example, I could ask you to find the equation of the tangent to the function f at the point 1 comma e. Remember, e is just an irrational number you studied back in algebra course. It's about 2.71828. It keeps going. It's like pi in that sense. It's an irrational number whose decimal representation never ends or repeats. But it's a number. It's basically a number. So we're looking at the point 1 comma e. So it's 1 comma 2.71828, on and on and on. Well, how do you find the equation of a tangent line? You take the derivative, that gives you the slope, and then you use the point, and you use the point slope form, and you write the equation. Well, we've already done the derivative, so the hardest part of this problem is already done. The point slope form is y minus y1 is equal to m times x minus x sub 1. In this problem, the x sub 1 is the 1 and the y sub 1 is the e. And the slope is whatever we get by plugging 1 in for x in the derivative formula. So if you plug 1 in for x, you get 1 times e to the 1 minus e to the 1 all over 1 squared. Well, 1 times e to the 1 is just e to the 1. So what you end up with is e to the 1, which is just e. You get e minus e up top. Well, e minus e is 0, so you end up with a slope of 0. That tells you it's a horizontal line. But if you plug it in, you get 0 for m, e for y sub 1, 1 for x sub 1, and when you simplify that, the whole right-hand side goes to 0, so you get y minus e is equal to 0, and if you solve that for y, you get y is equal to e. It's a horizontal line that goes through the number e, which is about 2.71828. Same sorts of questions we were answering in earlier sections. It just turns out now we can take derivatives of exponential functions, so we can throw those into the mix when we're working problems like this. How about this? Find the slope of the tangent line to y is equal to e to the x over 3 at the point 0 comma 1. We have a picture of what that looks like on the right, but the picture is not really necessary to solving the problem. First thing you do when you look at this is say, well, x over 3 might better be thought of as 1/3 x. When you're taking derivatives, it's easier to take the derivative of a number times x, or a number times x to a power, than thinking of it as a number, as x divided by a number. So anytime I see something like that and I know that I'm going to be taking a derivative, I tend to write x or x to a power divided by something is just multiplied by the reciprocal. So dividing by 3 is the same as multiplying by 1/3. So in my mind, it's much easier to think of this function as y is equal to 1/3 x instead of y equal x over 3. Only because I know when I take a derivative of the exponent, it'll be easier, because I can just use the power rule. So thinking ahead to that, I'm now ready to take the derivative. The derivative of e to a power is e to the power times the derivative of the power. So I write down e to the power, which in this case is 1/3 x, multiplied by the derivative of the power, or the derivative of 1/3 x. Well, of course, the derivative of 1/3 x is just 1/3. And most of us write the 1/3 first. It just looks more natural. So I would write that the derivative of y with respect to x is 1/3 times e to the 1/3 x. Now remember what we're doing. We actually want to find the slope of the tangent line at this point. So what we have to do is take the derivative, which represents the slope, but we want to plug in x equal to 0, because the formula says there's an x in the derivative. So you have to take that out and plug in the actual number. So at the point we're interested in, x equals 0, when you plug 0 in, you get 1/3 e to the 1/3 times 0. Well, 1/3 times 0 is 0. Any non-zero number raised to the 0 power is 1. So you're really just doing 1/3 times 1. So the slope is 1/3. This is the same sort of question we could have asked about problems from before we learned about derivatives of exponentials, but now that we do know how to do derivatives of exponentials, we can throw in exponential functions and ask those same questions. So there's very little new in this section. It's mostly just applying our same type of problems with a new type of function tossed into the mix, which means we can also do things implicitly. So you can see this problem where you don't have y equal to, it's not solved for y. It has an exponential component. It has an exponential term. So when you get to the derivative of that exponential, you'll have to use the new rule that we just learned. You know the first step for taking the derivative implicitly is you take the derivative of both sides with respect to x. That means you do it term by term. So you've got to take the derivative of x squared times y minus the derivative of the next term, which is e to the y, minus the derivative of the next term, which is 5, equal to the derivative of 0. Well, the derivative of any number is 0. And now you've got to go back and take the derivative of those three terms on the left. So start off with the derivative of x squared y. That's a product, so we'll be using the product rule. Product rule says take the first factor times the derivative of the second plus the second times the derivative of the first. So that would be first factor x squared times the derivative of y is dy over dx, plus then you take the second factor, which is y, times the derivative of x squared, which is 2x. Now you move to the next term, minus the derivative of e to the y. Well, you've got to go back to your formula. The derivative of e to any power is e to that power times the derivative of the power. So we've got y instead of u, so it becomes e to the y times the derivative of y. Then we move to the third term. Well, the derivative of a number is 0, so the derivative of 5 is 0, and we already have a 0 on the right-hand side. The next step in the, let's move that up a little. The next step in the process of finding dy over dx implicitly is to take the terms that have dy over dx in them and get them on one side and take everything else to the other side. So the two things I've underlined both have dy over dx's in them, so they stay where they are. The one thing that doesn't, that 2xy, goes to the other side and becomes a negative 2xy. Once you get the terms with dy over dx on one side by themselves, then you factor out the dy over dx. So you see there's a dy over dx here and here. If you factor it out, you're left with an x squared in the first term and an e to the y in the second term with that minus sign between them. Once you get to that point, all you do is divide both sides by the factor you want to get rid of on the left. And if you divide both sides by that, you'll get minus 2xy over the quantity x squared minus e to the x. Again, this is pretty much what we've done earlier, except we've allowed for the possibility of a function to be an exponential. This is probably as good a time as any to mention that you really do have to know how to use your calculator well enough for it to help you on these, what's going to turn out to be in a minute, these application problems that we're going to go through. So I want to take just a minute to point out a few things that might be helpful to you. For example, if you press the right combination of buttons on your calculator, you might get something that looks like this. A number with an exponent that might in this case be something like minus 0.04. If you see something like that pop up on your calculator, what does it mean? Basically, it's the calculator's version of scientific notation. Very specifically, the numerical part of the exponent tells you how many decimal places to move. So the decimal right now is sitting just to the right of 5. This is telling us to move the decimal place 4 places, and the sign in front tells us in which direction. If it's a minus, it goes to the left. If it were a plus, it would go to the right. So what this is telling us to do is take the decimal place in front of the 5 and slide it over 4 places to the left. And it's to the left because it's a negative sign. So that 5 to the negative 4 power, what that really means when it's written like that, 5 dot, and then you've got negative 04. That means to take the decimal place, and you can see it's been counted over 4 places, and it's going to the left because of the negative sign. If it were a positive 04, it would go 4 places to the right. Simple, but if you don't know what it is, you don't know what to do. So make sure you know how to deal with those. How about this? Have you ever tried to enter a negative number in the Casio FX260? You can't enter it directly. What you have to do is just put the positive value in, and there's a plus minus key on the calculator. You press that, and it inserts the minus sign. So if I wanted to enter negative 7, I would first enter positive 7, and then I would hit the key that's got the plus minus on it. And if you do that and look at your calculator display, you'll see immediately that a minus sign pops in front of the 7. You cannot enter a negative sign directly. You have to do it that way. Okay, we're talking about exponential, so the base e obviously comes up. And if you ever want to calculate a power of e, here's how you do it. You enter the power, then you press the shift key followed by that button that's got ln on the face of it and the e to the x above. And you can see it on the actual calculator I've displayed here. Let's see. There's the shift key, and there's the key I'm talking about. It's got ln on the face, and it's got e to the x above. And when you hit shift, it executes the function above the main button. So, for instance, if I wanted to calculate e to the 4th, you'd put the exponent, the power in first, the 4. I always do that first, and then do shift ln. And we're going to talk about ln. It's a natural log, and you've studied it in earlier algebra courses. But the shift part, when you hit shift, it executes the function above the key. So 4 shift ln means 4 on a base of e to the x. And if you did that, you would find out it was about 54.59815,003. And a problem might tell you to round it off to 2 decimal places or 3 or whatever. You do whatever the rounding tells you to do in the problem. Now, if you want to calculate e to a negative power, you have to incorporate the knowledge we have of how to put a negative number in. So what you have to do is put the positive 4 in, then press plus minus, which puts the minus sign in front of it. So if you look at your calculator at that point, it'll have a negative 4. And then you do your shift ln, which executes e to that power. And if you do that correctly, you'll get 0.018315638. And in a particular problem, they might tell you to round it off to a certain number of decimal places. But here I'm just showing you how to use the calculator. Simple enough, but it's something that you have to think about, because if you don't, you just look at the calculator, you may have trouble figuring out how to do it. Okay, having done that, let's get back to the problems we're going to work. Here's an application problem that says the demand function for a product is modeled by P equals 74 times e to the power of negative 0.000025x, where P is the price per unit in dollars and X is the number of units. I'm going to ask multiple questions, but the first question is, what price will yield a maximum revenue? And we'll round it off to the nearest cent. Well, maximum revenue means you have to take the derivative of the revenue function. But now P is not the revenue function. P is just the price per unit. You've got to remember from earlier work that the revenue is price times quantity. If you want to know what your revenue is from selling 100 things for $2 a piece, it'd be 100 times 2 would be $200. If you sold, 10 things at $50 a piece, that would be 10 times 50 would be $500. So the revenue is price times quantity. So they didn't give us the revenue function, which is what we have to maximize, but they did give us P, so all we had to do was say P times X. And remember, in this context, P is equal to this exponential, 74e to the minus 0.000025x times x. And it would just be more natural to put the x over with the 74. So that's our revenue function. We want to maximize revenue. That means we have to take the derivative of the revenue function, and since it's a product, we'll be using the product rule. The 74x is like the u, and the e to that negative power is the v. The product rule says you take the first one times the derivative of the second one plus the second one times the derivative of the first, and one of those factors is an exponential, so we'll also end up being forced to use the derivative of the exponential rule as well. So I put them both there. But anyway, going back to the product rule, we take u times the derivative of v. This is the u. This is the derivative of v. Remember, the derivative of an exponential is the exponential written down, so that we're looking for the derivative of e to the negative 0.000025x. So we write down e to the negative 0.000025x, but then we multiply it by the derivative of the exponent, and the derivative of a number times x is just a number, and the number happens to be negative 0.000025. That's the first half of the product rule. Then we reverse it and we take v, which is the exponential, multiplied by the derivative of u, and of course the derivative of 74x is just 74. Now a little bit of simplification is in order. For example, this number, this is just a number, and 74 is just a number, so why don't we just go ahead and multiply them together and put them out front. So if you did that, you could take 74 multiplied by that negative decimal value, and if you multiply it on your calculator, you'll get negative 0.00185, and then you've got the x and you've got the exponential. Then you've got the plus sign, and I would just recommend putting the 74 in front. That's the typical way of doing it. So that's the derivative of the revenue function. What do? You take the derivative and set it equal to 0. Now when you've got an expression, a complicated expression, a higher order expression, set equal to 0, one of the first things you might try to do is factor. And if you notice, you have the exponential in both terms, so you can factor it out. So if you factor out that exponential, in the first term, you're just left with the negative 0.00185x, and in the second term, you're just left with the 74. Now you know if the product of two things is equal to 0, either one or the other of them has to be equal to 0. So either e to the negative 0.000025x is equal to 0, or the other factor, negative 0.00185x plus 74 is equal to 0. Now if you try to set the first factor equal to 0, think about it a minute. E is a number. It's about 2.71828 raised to a power. How can you take a positive number that's a little bit less than 3, raise it to a power, and ever hope to come up with an answer equal to 0? And the answer is you can't. You can't take a positive number to any power and ever get 0. So when you look at that, you say, okay, there aren't going to be any critical numbers coming out of that because there's no real number that I can raise to a power of e and ever get a 0. And that's not true just for e, that's any positive number. If I tried to take 7 and raise it to some power to get 0, that's impossible. 3 to any power, you can't get 0. You can't take a positive number, raise it to any power, and ever get 0. But now the second factor, if you set it equal to 0 and solve for x, it comes out actually to be 40,000. So that's our critical value. If they had just asked, what's the quantity that yields maximum revenue, then it would be 40,000. But they actually didn't ask. They asked what price will yield maximum revenue. Well, price is that original function they gave us when we first started off. So I wrote that down. I have to plug 40,000 into that to figure out the price. The quantity to produce maximum revenue is 40,000. They didn't ask for that. They could have, but they didn't. They asked for the price that would yield maximum revenue. So you have to take that 40,000, plug it back in for P. And this again is where you have to get pretty good with your calculator. So you want to multiply the two exponentials together, remembering that you've got a negative times a positive, so it'll be negative. And believe it or not, when you multiply those two numbers together, you get -1. So you end up with 74e to the -1 as being the price. You want to get it rounded to the nearest cent, so you'll have to use your calculator to calculate that. And what do? Well, we talked about that a minute ago. In that calculation, you want to calculate e to the power of -1. You can't plug in a negative number directly, so you have to put in the +1. Then you got to press the plus/minus key. That turns it to a negative. Then you want to raise it to the power of e, and we talked about earlier how you do that. You do Shift LN. Then you want to take that and times it by the number out front, which is 74. So if you times that by 74 and press equal to, you'll get 27.22307.865. Now, it's not necessarily just a natural thing to be able to calculate this in your calculator. So please take the time to practice this skill so that when you get under pressure on a test, you don't just panic and just wipe your memory and don't remember how to do it. You need to practice. Practice makes perfect. Practice the skill and you'll have it. If you do it once or twice, get to the test, panic, and you've forgotten. Please practice. And then finally it said round it to the nearest cent. So that would be about $27.22. That's the price per unit in dollars if you want to maximize your revenue. I'm going to clean that up and push some stuff out of the way because there's a second question coming. So we found out earlier that the price was $27.22. The next question is going to be about, it's going to be about what the maximum revenue is at that price. But we're going to need to refer to some of the information that we produced earlier. So I put up something I called a summary. From earlier, we found out that the revenue was 74x times e to the minus 0.000025x. And again, I've wiped it off now, but we found out that the maximum revenue occurred at 40,000 units. So if I want to know what the maximum revenue is at that price, all I've got to do is take 40,000 and plug it in for x into the revenue function. And in theory, that's the best way to do the calculation. But in practice, because we've already found the price per unit and the number of units, and because we know that revenue is just price per unit times quantity, we've already done some of the calculation heavy work. So the in practice best way to answer this question is not to plug the x value back into the original total revenue function, which would give you total revenue, but just use the work you've already done and cut down on the arithmetic a bit and just do price times quantity. And if you take the price per unit, which is $27.22, and multiply it by the quantity that produces maximum revenue, which is 40,000, and if you round it off to the nearest dollar, which is what the instructions said to do, you get $1,088,800. And that's easier in practice than going back to the original revenue function and plugging in x, which would also give you the maximum revenue. How about this? The demand function for a product is modeled by A equals 6,000 times e to the 0.07t, where t is in years. Find the rate to 2 decimal places at which the balance is changing when t is equal to 1 year. Well, they ask about the rate. Anytime you have a rate of change, you're going to take a derivative. So you're going to take the derivative of that. If you have a number times the function, the derivative is just a number written down times the derivative of the function. So you just write the 6,000 down and multiply by the derivative of e to the 0.07t. The derivative formula for the exponential says you write the exponential down and then you multiply by the derivative of the exponent. Well, the derivative 0.07t is just 0.07. If you multiply 0.07 times 6,000, you get 420, so you end up with 420 e to the 0.07t. They want to know the rate at 1 year, so you just plug a 1 in. Everywhere there's a t, there happens to just be one t. So you end up with 420 e to the 0.07. Again, this is the skill I've asked you to practice over and over again. I hope you're doing that. So the first thing you want to do is type in the exponent, which is the 0.07. Then you want to do shift ln, which gives you the natural log. And that gives you the answer for this much. But then you want to times it by 420. So you put times 420. And to make it evaluate that product, you have to hit equal to. When you do that, you'll come out with 450.45 rounded to 2 decimal places. Please practice quite a bit to make this second nature to you. Same problem now, except t equal 10 years. So we take the same derivative we already found. We don't have to do it over again. But this time plug 10 in. Well, 10 times 0.07 is just 0.07. And to calculate that, it's the exact same calculation as we did earlier, with one exception. We do 0.7 instead of 0.07. So when it's 0.07, you put in that. When it's 0.7, you put in that. Otherwise, it's exactly the same calculation. And when you press equal to and round it to 2 decimal places, you'll get 845.78. So practice these things. Go do these problems as soon as you can while all this is fresh on your mind. Make sure you've got the Casio FX260 so you can practice as you go through here. Using another calculator to do it is a bad idea. You are not allowed any calculator but that on the test. So it's a bad idea to practice with any other calculator. Just a really, truly bad idea.